To solve real-world problems in engineering and physics, we often deal with systems too complex for exact calculation. We rely on simpler approximations that computers can actually process. The full space, X, contains our exact target vector, X. The 2D plane, Y, represents simpler solutions we can actually compute. We measure the distances between X and points on Y. The absolute minimum distance, delta, identifies our best approximation, Y0. Defining this minimum distance translates an abstract search into a precise optimization problem. It gives us a mathematical target to hit, which is how numerical analysis algorithms process large datasets. In infinite-dimensional spaces, a best approximation might not actually exist. The distances might get smaller and smaller without ever reaching a minimum. To guarantee a solution, we must prove it exists for finite-dimensional subspaces. Since the origin is in our subspace, the best distance delta cannot exceed the distance from X to the origin, the norm of X. We restrict our search to a closed ball E with twice this radius. Any point outside E is farther and useless. Because our subspace has finite dimensions, this closed area E is compact. The distance function, the norm, is continuous. A standard principle of analysis states any continuous function and a compact set must reach its absolute minimum, guaranteeing our best approximation, Y0, exists. By setting a firm boundary based on the origin, we eliminate infinite space from the equation. We know exactly where the optimal solution lives. Let's look at how this applies to a specific environment, the space of continuous functions on a closed interval, using polynomials as our simpler subspace. This illustrates uniform approximation. We want to fit a smooth polynomial curve, y of t, to a complex continuous curve, x of t. We find the largest vertical gap between them. Since polynomials form a finite-dimensional subspace, a polynomial exists that minimizes this maximum gap. We can confidently write algorithms to find this polynomial. Knowing the solution exists means resources spent on curve fitting will converge on a reliable answer. We know a best approximation exists, but is there only one? If we change how we measure distance, the answer is no. This coordinate system displays the L1 norm, often called the Manhattan distance, where we only move in rigid horizontal and vertical steps. Our target point X is at 1, -1. Our subspace Y is this diagonal line, where the coordinates are equal. Under these rules, X does not have a single closest neighbor. If you measure the L1 distance from X to any point on this highlighted segment, the total length is always exactly 2. Every single point on that line segment is tied for the title of best approximation. This happens because of the underlying geometry of the space. These two shapes represent the unit spheres for different norms, the set of all points at a distance of exactly 1 from the center. On the left is the L1 diamond. On the right is the standard Euclidean circle. To guarantee a unique solution, a space must be strictly convex, meaning its unit sphere has no flat sections. The diamond has flat edges, allowing a subspace to slide up and touch multiple points simultaneously. The perfectly round circle can only ever touch a subspace at exactly 1 point. Finding an approximation is guaranteed by the dimension of the subspace, but finding a single, unique answer requires the rigid, curved geometry of a strictly convex space.